So last time we talked about different types of logic devices. These are types of logic gates. What is this logic gate that I'm pointing to here?
An and.
And, very good. And what's the other one? What's this one?
Or.
Or. Okay, can you see my scribbles okay? Is everything showing up?
Yes, sir.
Yeah, it all looks good.
Okay, great. So this is a little bit more sophisticated device than what we talked about. And it's a certain type of device called a multiplexer, and we'll see why in a second and how it works. But if you see something like this, the question is, how would you figure out what it's doing? How do you know what it's up to? So we'll create this thing. What do we call this thing again? That's on the right.
It's the truth table.
It is a truth table, yes. So truth table, we want to remember that. So the best thing to do is to fill out the truth table. Now, what did I command you when I talked about how we fill out the truth table? There's a certain way I want you to fill out the inputs.
To use the binary sequence.
Thank you, Adam. Yes. We're gonna count in binary to fill out this truth table. So 0, 0, 0. These are the inputs. There are 3 inputs: D0, select, and D1. Okay, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And then we can just go through and step by step figure out what's going on. So what's this guy here? This is called
the inverter.
The inverter.
An inverter. Very good. So it just changes the state to the opposite state. It's also can be known as a buffer. There we go. In this case, it would be an inverting buffer. Sometimes what is it that makes it invert? Is it the triangle or the little circle?
The little circle.
The little circle, okay? So if we saw the triangle without the circle, it would just be a buffer. And what that is doing is, that might be used to help step up the voltage to something. You know, we talked about how your logic voltage levels might get drained, or there might be noise or something like that, and the buffer would just help reconstitute your signal. An inverting buffer actually changes the sign of changes the state. Okay, so this line, it's helpful to draw, and I've already done this already. I put O0 and O1, so that's like out 0 and out 1. This line right here is the not S. Okay, so this column should be easy to fill out. So it's just the opposite of what S is. So 1, 1, 1, 1, 0, 0, 0, 0. Now we can fill out the column for O naught. And this is an AND gate. So anytime we have the S naught column and the D0 are both high, then out O0 will be high. So that happens right here, and it happens nowhere else. No, right here. And the rest will be zeros. Okay, and then O1, its output is a combination of S and D1. So when S is high and D1 is high, its output will be high. And then the last step is the OR. So if either O naught or O1 are high, it will be high. So now we can look at what is actually happening here. What is this device doing? Well, we see that when select is set to 0, the output is the same as D0. See that? We get this and this. And that's because the output is selected to, the select is set to 0. If the select is set to 1, we get that the output mirrors D1. Okay, so this circuit is allowing you to select between two different inputs. So by controlling the S line, you can pick to either pass along D0 or pass along D1. That's a multiplexer. And you can have, this is just a 2-input multiplexer. You can have many more inputs. Okay, so that's the solution to that. So kind of a cool device. That's how logic gets used. Yes, question?
Would that be kind of similar to like if you have 2 light switches in a room where like they both can turn them off, the lights on and off?
No, because what you're, I mean, that's like an OR gate. That's like a physical embodiment of an OR gate, but not what's going on here. Here you're selecting that you're going to take the input from one source or another source. You're not combining the 2 inputs, you're selecting between the 2 inputs. So you might have, imagine you had like a trainer aircraft where there's a pilot and an instructor and an instructee, and you wanted to be able to switch the controls from one person to the other, so that the aircraft responded to only one pilot at a time. Might be more akin to, you might use a system like this. Okay, on that. All right, so for today, we are talking about combinational logic or sequential logic. So what we talked about in the last lesson and we just reviewed are devices that do not depend on time or timing. They are, if you change the state at the input, then the output will change. There's no sequence that has to happen. There's no timing that goes on. Today we want to add that complexity of timing. And this chart gives an introduction to that by just talking about what would happen as things change with time. So what type of gate is this?
That's an
Okay.
and.
That's an and.
AND gate. Okay. So what we're seeing here is this is time. Proceed, we're proceeding in time. So time is going this way. And what we're showing are the various inputs. So there's an input A and input B. And so this is indicating that when things start out, A is low, it's at 0, and B is high, it's at 1. As time proceeds, B stays high, then A goes high. And so what would happen at the output? Well, if both A and B are high, then the output should be high. So right here, this is 1, this is 1, and so the output is 1. Then A goes back low, so the output has to go low. Then A goes back high, output goes high, et cetera, et cetera. Here, B goes low, the output's low, B stays low, so the output has to stay low the whole time. So these are helpful for visualizing how the device changes over time in response to different inputs. So we'll see more of these coming up here the rest of the lesson. All right, so one of the most simple types of sequential logic devices is a latch. So this is a D latch or a data latch. And what's different about this compared to what we talked about last lesson is this clock. Okay, there's something called a clock input, and it controls when the device actually changes its state. So here's the truth table for the latch. It's very simple in that the output is known as Q, and then we have a Q naught, which is the opposite of the output. And many of these, this is very typical for these type of devices. They'll usually have a Q and a Q naught. But we mostly care about what the output is doing, the Q. So if D is 0 or if D is 1, it just passes out whatever D is. So it's just passing along the input D to the output, with the caveat that it only passes the output when it gets a clock pulse. So the way this would work is you have a timer in your microcontroller or other device that's sending, usually like a square wave, a steady train of pulses to the device. And it only passes the information along when it receives a clock pulse. The key thing here, what is this arrow about? Does anyone know what this upward arrow is? It's okay. So we have these clock pulses. Exactly when should the device be triggered? This clock pulse has a bunch of different features. Well, we want to specify very clearly when the change happens. The arrow means a rising edge. So when it sees the signal start to go, so if the signal is moving this way and it sees this start to go from 0 up to 1, that's a rising edge. So the up arrow means that it will trigger on the rising edge of the clock pulse. Now, sometimes you have devices that are working, so like in your computer, you have millions of calculations happening per second, and those all have to be precisely timed so that they happen at the right time and they happen correctly. Certain things have to happen in certain orders. So you have a clock, and when you talk about the speed of your laptop, like it's 2 gigahertz, that's the clock speed of the laptop. That gives an indication of how fast these operations can happen. And so in that case, you've got this steady train of pulses coming through. Sometimes you have devices where you don't want to trigger them all the time. You just want to trigger them at a certain time. And so you might just have a single pulse happening occasionally when you need to turn on that device. But what this truth table is indicating is that whenever we receive a rising clock pulse, we will just pass whatever is at D, we'll pass it to Q. And this last line indicates that if we don't have the clock pulse, the output will just be whatever the previous output was. So Q naught means previous output. Okay, so that's the simplest sequential logic device. We're about to get a lot more complicated. Okay, one thing that's cool about these types of devices is that this is where we get into memory and the ability of devices to remember things that happened or tell you information about what happened in the past. So this is known as an RS latch, and what this looks like in a circuit diagram would just be something like this. It would just have an R input, an S input, and then usually like a Q and a Q naught. Not whoops. I'm not gonna do that. Oh no. I think PowerPoint's about to crash. Let's try to talk through this while it's crashing. So I meant to just put a bar over that or a tick mark to note that it's not Q. So this, what is this logic device here?
That's
You
an
might-
OR.
Yeah.
invert.
So that's a NOR. Man. Where were we? Okay. What about that football game? Was that like the best football game you guys have ever seen in person? Like, I mean, at least Air Force game? And not a good game in the sense that it was like competitive, but to see one of your rivals just get shellacked. Have you ever seen a lopsided victory like that?
Yeah, that was pretty cool to see Navy just kind of get destroyed.
Yeah, especially because we've just struggled with them so much. I was really surprised because I thought, usually we play a tune-up game, we play like Central Ohio Community College or whatever, and our players get a chance to get some game time. And we didn't have that this year. So I was surprised to see that the team did so well. There was a funny comment watching it on TV. The commentators are like, well, it's good to see so many of the students there supporting the team. And I always get a kick out of those comments because you would think that someone would have told them that it's mandatory for you guys to go to the game, but maybe they don't want to say that out loud on camera. Okay, where were we? So we had this diagram of the latch RS, Q, not Q, and we have inputs and we have outputs. Okay, this is a NOR, and the way a NOR works is like it sounds. So let's write a truth table for the NOR. You have some inputs A and B, and then you have an output O. So 0, 0, 0, 1, 1, 1, 1. And an OR gate would mean anytime you have a high input, the output is high. So then we just invert that. So for a NOR, its output is this. Okay. So this is a cool device because it remembers. We'll talk about how this works in a second, but let's just look at the truth table for now. So when the inputs, both the S and R, so S stands for set and R stands for reset. So we can set the device, meaning we set the S input to 1, and that makes the output 1. So this is set, and that'll make the output 1. And the output will stay whatever it was. If you look at this column, in this scenario, if we don't touch the reset, so if reset stays at 0, so this case and this case, the output will stay 1. Latch means that this is another way of saying that Q naught, meaning Q doesn't change. It retains the previous state. And in this case, Q naught retains the previous state. So what we see here is that as long as the reset is still 0, we can change the set, we can change the input as much as we want, it doesn't matter. It will stay whatever it was. it only changes its state if we reset it. So this is reset. When we set R to 1, we've reset the device and the output will go to 0. Now, the way this actually works is a bit tricky. So imagine we start out with everything is 0. And in this case, S and R are 0 and Q is 0. So if Q is 0, we have a 0, 0 entering this NOR gate. And from our truth table, that means the output of this will be 1. Okay, so we're starting with 0, 0, 0, 1. And so let me switch pens. So the output is Q is 0, so the output of the device is 0. If the first thing we would do is to set it. So we set it by making this go to a 1. So on this NOR gate, we have an input of a 0 here and a 1 here, and that's going to make this output change to a 0. And so now we have a 0 here and a 0 here, and this will change to 1. Okay. So by setting the device, we set a 1 and a 0, and we get an output of a 1 and a 0 here. So in this state, Q is 1 and Q naught is 0, 1 and 0. So Q is at a 1, so it's right here on this NOR truth table. In order for it to change back to 0, one of its inputs has to go back to 1. But the Q naught can't change to 1. Only the reset can change to 1. So even if this S changes back from 1 to 0, nothing changes on this output until R goes to 1. Once R goes to 1, then we can reset the device because Q naught will go back to, I'll change the red here. If we set this to 1, then we've got an input of 0 and 1. So this will go to 0. And here we have a 0 and a 0. And so this can change to 1, and we're back to reset to where we were before. And so until we set it, it won't switch back again. So by designing this circuit in this way, the output will only change given certain input conditions, and that means it can remember what the last state was. This diagram on the right is showing a timing diagram of this device working. So look at the top half of the graph at first. There's two scenarios we'll talk about. There's ideal timing, meaning that there's 0 delay in when things switch. So here, if we look at the truth table, notice both of our inputs, S and R, are 0. So that means that the outputs will retain their past state. So Q is starting at 0 and Q naught is starting at 1. So they'll stay that way until something changes. So the first thing that happens is S goes high. So this is a set. So we're setting the device there. So Q should go to 1. You know, we see that in this row here. Q goes to 1, Q naught goes to 0. Now, as I described, the set can change back to 0, but the output is not going to change until we reset. So over here is the first reset command, and then we see Q and Q naught flipped states, okay? And once it's reset, the R can do whatever it wants. It's changing, but it's not going to change back until set goes high. And since there's no set, set is low here, so we're not getting any change on the output. The lower figure is showing what would happen more realistically is that it takes some time for these changes to propagate through the device. So when we get the set command, Q naught doesn't instantly change. It takes a little bit of a delay before it changes. So it goes low, and then it has to go low before Q can go high. So we get this gap in timing between when we set it and when the output actually goes high. So that's something to keep in mind in real devices, and sometimes that can make a difference in what the output is. And we'll see that in some homework coming up. Okay, moving on. So another problem that we can take care of with these types of devices was called voltage bounce. And this is, we're going to actually see this in the lab. You're going to test this, and you're going to verify that voltage bounce exists, and then you're going to design a circuit to overcome that. And you'll actually do some tests with your Arduino that demonstrate how that works. No, don't do that. So, oh no. Well, I was trying to pull up a video and the video is unavailable, it says. Okay, so I was going to show you a bit of video that shows the bouncing happening in real time. Okay, so when you have a mechanical switch and you flip the switch like a light switch, it doesn't cleanly change from low to high or zero voltage to high voltage. In reality, what happens is you get this bounce that happens. So it flickers between high and low before finally settling on the new state. There's two reasons it does that. One is there's mechanical vibration, so it mechanically bounces, and the other is electrical arcing. So either of those will cause the input that is sensed by the device to go up and fluctuate up and down. For turning on a light switch, we can live with that. There's no problem with the light momentarily flickering on and off before it settles on being on. But in a digital logic device or a computer, this could be devastating. We're going to see in the lab, you're going to create a system that counts how many times a switch changes position. And if you needed to do that, this bouncing would really mess you up, because in this case, it should only record one switch, but instead it's getting 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10 switch flips, which is not what we want. Okay, so this is a circuit that's designed to overcome that problem, and it's called a debouncer circuit. So this looks similar to what we just talked about with the latch, but it's using NAND instead of AND gates. Okay, and so again, we should write out the truth table for the NAND. And we have an input 1 and input 2, and we have an output 0, 0, 0, 1, 1, 0, 1, 1. So here, we would, if it were an AND gate, we would only get a high value right here, but it's NAND, so we flip it. So the only low value is when both inputs are high, and all the other inputs are high. Now, what's going on? What's this over here? The 5 volts and the resistor and a switch. What does this look like to you? What is that?
Pull down and pull up resistors.
Yeah, these are pull-ups, right? These are pull-up resistors. So that's what's going on. So we see that when the switch is in the low position, A reads how much? So when the switch is down here, what is A reading?
5 volts.
5 volts. It's reading high. And what's B reading?
Low.
Low. Very good. Okay, thank you. So B is low, and that's the initial state of this system. We're going to flip the switch from B to A, and if we did this with a mechanical switch, we would get this bouncing, and you're going to see that in the lab. So in this case, so A starts high, so this is a 1, and Q is low, so this is a 0. So that means this must be a 1 over here. And this is low. So if we have 1, 0 on our input, this output must be 1. And so we have 1, 1 on this input, so its output is 0. Okay, so A starts high and Q starts low. This is high and this is low. So we're here with this is high, this is also high, Q low. So the state of Q can't change until, so both of right now, both inputs to this NAND gate are high, and it can only change if one of these inputs goes low. A will eventually go low when we get the switch closed, but we're not there yet. So initially, Q naught is 1, and it can't change back to 0 until both of its inputs are high. So it can't go low until Q goes high and B goes high. And that won't happen until the switch starts to close. Once the switch starts to close, then Q will go high. So this would be high and this would be high, and Q naught will go low. And once it's low, it's going to lock A into being high. So we see that here in the timing, notional timing diagram. As we first start to move the switch, we're going to get bouncing on the B line, but Q won't change until A starts to go to 0. And once that first happens, Q goes up to 0, and it's latched in the, Q goes up to 1, it's latched in the high state. And it has to stay that way until both of its inputs are high, and that could only happen if we move the switch in the other direction. So this type of a circuit gets rid of this effect of this bouncing and keeps it so we get a clean transition from low to high. You're going to build this in the lab and experiment with it and see how it works. Okay. Moving on here. Okay, so last lesson we talked about simple logic gates. They're the building blocks of logic circuits, and they do decision-making operations. Flip-flops are an extension of gates. They include gates, and their function is to store information and basically give us the ability to have memory with our devices. Okay, so we talked about this earlier. Whoops, that's an extra S. Edge triggering. So you've seen this symbol on the logic diagrams, this CK or CLK, that's a clock pulse. So if you see this arrow with no dot, that means it is a positive edge triggered. So when the clock signal goes from low to high, that device is triggered. That's a rising edge or a positive edge triggered. If you see this dot here, that means it's negative edge triggered. Okay, and it waits for the falling edge to be triggered. And this is critical because these devices, we want them to operate extremely fast, and we need the ability to precisely time when things happen. Okay, so we saw the SR flip-flop before, and with this version of it, it's the same internals as the previous SR we looked at, but these are triggered with a clock pulse. Okay, so it's either positive edge triggered or negative edge triggered. So we have the same truth table, but we have this new column for the clock pulse, indicating that, so this is a positive edge triggered device, and it only changes state when it gets that rising edge. So again, to reinforce this point, this is the same device we had on the previous screen. We have an up arrow, so it's a positive edge triggered flip-flop. So it has the same logic function as the basic SR flip-flop, but it only responds when it gets the positive pulse. So here we have S and we have R, so we have, this is set and this is reset. Both are starting low. We hit reset. The Q is high, so it's already been set. We want to reset it, so we flip the R to 1, but nothing happens. You know, if we were to follow this down, we see nothing changes right here. It doesn't change because it needs to get that positive clock pulse. So this is staying high, and when the positive clock pulse happens, that triggers the change. Does that make sense? This seems like overly simple to me, but I want to make sure you guys are following it. Okay, Kevin's got 2 thumbs up, so he must really be following along. Okay, again, this is, what would we call this right here? What is this event?
A falling edge?
Falling edge, very good, or negative edge. And a falling edge doesn't do anything with this device. So here we're trying to set the flip-flop, but since there's no positive clock pulse, it doesn't set. Okay, that can't happen until we get another clock pulse. So one way to analyze a device like this is to just look at the clock. You can ignore all these inputs except for the cases where you're getting the rising edge. In this scenario, there's only 2 places in this plot that you even need to pay attention to. Right here and right here. So you can look at when this gets the positive edge, what are the states of everything else? Well, Q was low, so it means we're right here. S was low and R was low. So we're up here where S and R are 0 and Q is low. Then we get the clock pulse. Set goes high, so we're 0 and 1, and so it should, all right, yeah, we're 1 and 0, so it should set, and Q should go up on the rising edge. Okay, and then when there are no other rising edges in this graph, so there's no other changes to the device. Okay, these are very simple devices. This is a D flip-flop, a data flip-flop. This is what I showed at the beginning of the lesson. It just transfers the input to the output on the clock, on the positive clock pulse. A toggle flip-flop is very similar to that. But what do you think the toggle flip-flop does? Anyone? Any guesses on what a toggle flip-flop does?
maybe it just doesn't care what input is coming in. It just flips it every time it hits a clock signal or something like that. I don't know.
Yeah, it toggles. Okay, so when it gets the correct clock pulse, it will just switch its output from whatever it was previously. So in this case, what type of triggering is this?
Negative set, negative edge.
Yeah, it's a negative edge triggered. So if T is 0 and we get a negative clock pulse, Q will be 1. And if T was 1 and we get a negative clock pulse, it'll be 0. If we don't have a clock pulse, it doesn't matter. Q will just be whatever the previous Q was. Okay. Okay, so the next device is a version of a toggle flip-flop. It's known as a JK flip-flop. So this is a circuit that's composed of several JK flip-flops, but let's just talk about the JK flip-flop for now. So its truth table is shown right here. Can you see that okay? Not sure if you can see that.
Yeah, it's okay. Not great,
Oh,
but
we're
yeah,
over.
it's still readable.
Okay, time's up. I just realized that. Sorry about that. So what this does is it toggles just like the toggle flip-flop, but it has 2 inputs instead of 1. So we can tell it to load a 0 or load a 1, or tell it just to toggle its state. And this circuit I am showing you here is a cool device that basically allows you to count the number of clock pulses. So it takes time to propagate the clock pulse down to the last line, and by doing that, note what do you think? What is LSB and MSB? This is least significant bit and most significant bit. You may remember that from our reading on binary and number bases. So this is actually counting in binary. If you look at the Q outputs as Q0, Q1, Q2, Q3, this is the most significant bit. This is the least significant bit. And here we have 1, 1, 1, 1. So that is the number 15, meaning that 15 clock pulses have passed by. And you can look at this at any other state. Here we have 0, 1, 0, 1. So that's indicating 5 clock pulses have gone by. Is that right? No, that's 0, 1, 1, 1. Whoops. 0, 1, 1, 1. So 7 clock pulses have gone by. Okay. All right.